Good morning, everybody. Hope you're all healthy and safe. We are going to continue with the study on properties of ortho projection. So, in the previous lecture, we had introduced what is an ortho projection. It is actually a projection which also satisfies the property of symmetric. That is, and we studied few properties. Now, today we shall be continuing with the same. That is, we are going to discuss few more properties of ortho projections itself. So the first one is actually if P1, P2, etc. are ortho projections and P1, P2 is equal to P2, P1 equal to P, then P is also an ortho projection and the image of P is nothing but E1 intersection E2, where E1 and E2 are images of P1 and P2 respectively. Okay, so we need to show two things. One is that P is an ortho projection and the other E is nothing but the intersection of E1 and E2. So let us see how we can prove it. So we are given that P1 and P2 they are commutative, that is P1 P2 equal to P1 P2 equal to P2 P1, and suppose it is equal to P, we need to show that this P is a ortho projection. So first let us consider P square, that is nothing but P1 P2 square. So I can write this as P1 P2 P1 P2. Now just making some arrangements. So this is P2 P1 P2 P1 is nothing but P1 P2. So this is P1 square P2 square. P1 and P2 are ortho projections, so they are projections. So this is P1 P2. Now P1 P2 is nothing but P. So I get P square is equal to P. So P is a projection. Now I need to show that it is actually an ortho projection. So for that I need to prove that it is symmetric also, right? So let's see how we can do the symmetric part. Now inner product P of xy will be inner product P1 P2 of x comma y. This is nothing but inner product P2 of x comma P1 of y, because P1 is an ortho projection, and this is nothing but x comma P2 P1 of y, because P2 is also an ortho projection. And as P1 P2 is equal to P2 P1 is equal to P, I get this is inner product x P1. Therefore P is symmetric, right? And hence, as it is a projection which is symmetric, P is an ortho projection, right? Now next we need to show that E, which is image of P, is nothing but E1 intersection E2, right? E and E1 intersection E2 are same. So let us choose an element in E1 intersection E2. Okay, this implies X is an element of E1 and X belongs to E2. Now this implies P1 of X is equal to X by the projection property, and P2 of X is equal to X, right? Now let us see what is P of X. Okay, P of X will be nothing but P1 P2 of X. So this is P1 of P2 of X is X. So this is P1 of X, and this is again P1 of X is again X. So I get P of X is X. This implies X belongs to image of P, which is equal to E. So what have we got? E1 intersection E2. When I chose an element in E1 intersection E2, it was an element in E. So this one inclusion is satisfied. Now let's see the other one. So let x element of E Okay, this implies x is equal to p of x. Alright, so this is p1 p2 of x. Okay, p1 p2 of x. So this is actually p1 of p2 of x. This implies this is an element of e1, and similarly x equal to p of x, I can write this as p is equal to p2 p1 of x. So this is p2 of p1 of x. So this is an element of e2. Therefore x is an element of e1 as well as e2. X will be an element of e1 intersection e2. Hence e is contained in e1 intersection e2. So with the help of both these inequalities, both these inclusions, we can prove that the e is nothing but same as e1 intersection e2. So this was the first property that we have discussed in today's lecture, that is, if p1 p2 equal to p2 p1, where p1 and p2 are projections, it is equal to p, then that p is again another projection. Okay, that is, if p1 and p2 are projections, then p1 p2 is also a projection, and p2 p1 is also a not only projection, it is an ortho projection. And moreover, e will be the intersection of the image set. So that was property, the first property that we have discussed today. And now let's see the next one, and this is the last property of ortho projections. So the property states that if p1 p2 is equal to p1, then e1 is a subset of e2. Here pi's and ei have the same meaning, that is, p1 is an ortho projection, e1 is image of p1, p2 is another ortho projection, and e2 is a image of p2. Now if p1 p2 is equal to p1, then e1 is contained in e2 and p1 is less than or equal to p2. Okay, so these are the two conditions that we have to prove, that is, e1 is contained in e2 and p1 is less than or equal to p2. Moreover, the converse also, that is, if p1 is less than or equal to p2, then p1 p2 is equal to p1, and if p1 p2 equal to p1, then by the first property we can get that e1 is contained in e2. So let's move on to the proof of this property, the last one, that is, we are given that p1 p2 equal to p1. Given p1 p2 equal to p1, we will show that p1 p2 equal to p2 p1. Okay, this is what we are going to show first. So now let us consider inner product p1 of x y. So this is nothing but inner product p1 p2 of x comma y, right? Because p1 of x, p1 is same as p1 p2. Now this is equal to p2 of x comma p1 of y, that is equal to x comma p2 p1 of y, right? So what I get is, I get p1 star is nothing but p2 p1. Okay, p1 star is equal to p2 p1. Now p1 is an ortho projection, so let me just write it down. Since p1 is an ortho projection, p1 equal to p1 star. So this implies I get p2 p1 is equal to p1. Therefore, what have we got? We have got p1 p2 equal to p2 p1 equal to p1. So now here we shall use the previous property. Okay, so by previous property, p1 is an ortho projection, right? if P1 P2 is equal to P2 P1 equal to P, then we proved that P is an orthoprojection. So P1 is an orthoprojection, and also E1 intersection E2 is equal to image of P by property. So here it will be image of P1, that is E1. So E1 intersection E2 is equal to E1. This implies E1 must be contained in E2. Okay, so if we have obtained that E1 is a subset of E2, now we need to show P1 is less than or equal to P2, right? This is what is left to prove. So for that, what I'm going to do is, first I'm going to consider P2 P minus P1 whole square. So this is nothing but P2 square minus 2 P2 P1 plus P1 square. P2 and P1 are all orthoprojections, and this is equal to P1, right? And this is P1. So this is nothing but P2 minus P1. So P2 minus P1 is again an orthoprojection. Projection. Now let us consider or calculate what is P2 minus P1 of X, comma P2 minus P1 of X. This is equal to inner product X comma P2 minus P1 whole square acting on X. Now P2 minus P1 was a projection, so this is nothing but P2 minus P1 of X. Okay, so what I get is inner product X comma P1 minus P2 of X. Okay, this is equal to norm of P2 minus P1 of X square, which is always greater than 0. So from this I get P2 minus P1 is greater than equal to 0, and which implies P2 is greater than P1. Okay, now we shall see the converse part. So that is, conversely, suppose P1 is less than equal to P2. What is to prove? We need to prove P1 P2 equal to P1. Okay, or this implies P1 P2 minus P1 is 0, or that is P1 P2 minus I, or any of these. So here we'll be doing this part. Okay, so let's see how we can do that. Now P1 is less than or equal to P2 implies P1 minus P2 is less than or equal to 0, which further implies P1 inner product of P1 minus P2 of X comma X is less than or equal to 0. Okay, also norm of P1 into I minus P2 of X whole square is nothing but inner product. I'm just opening this. Okay, this is P1 I minus P2 of X comma P1 I minus P2 of X. So now this is P1 into I minus P2 of X. So P1 is less than or equal to P2. Okay, so I can write this as less than or equal to inner product P2 of I minus P2 of X, right? Since P1 is less than or equal to P2. Now what is this? This is nothing but P2 minus p2 square is again p2 acting on x comma p1 I minus p2 of x. p2 minus p2, this is 0. So this is inner product 0 comma p1 into I minus p2 of x. So this is 0. So what have we got? We have obtained p1 norm of p1 into I minus p2 of x square is less than equal to 0. So this implies norm of p1 of I minus p2 of x is less than equal to 0, but we know that norm is always greater than 0. Norm of p1 into I minus p2 of x is greater than 0. Therefore, what do we get? p1 into I minus p2 of x will be equal to 0 for every x. This implies p1 into I minus p2 is nothing but the 0 operator. This implies p1 is equal to p1 p2. Okay, now if p1 p2 is equal to p1, then we know how to show that e1 is contained in e2. Just now we have seen, using the previous property we can easily show that e1 is contained in e2. So these are the properties of orthoprojections. We have discussed them in 2 lectures, and so with this we shall wind up our section 6.4 also. So just go through all the properties of projections and orthoprojections. So thank you all, stay safe and stay healthy.